Okay, this is the last hour of Physics 1C for October 11th, and now we're going to moving on to talking about how you combine together resistors in a circuit, and then we're going to learn about Kirchoffs rules, which are a really powerful way to analyze circuits. Yeah, let's get going. So, combinations of resistors. So let's start off with series. If I have some resistors that are connected up like this, so one resistor here, which I call R1, connected up to another resistor here in series that I call R2, and we connect both of them to an EMF source here that we'll say has a terminal voltage that we call delta V, and flowing through our circuit we have a current that's called I. This. Our goal is to say, suppose that I want to take these and to merge them down just as we did with our capacitors into just one resistor that we call the equivalent resistance for the circuit. How do we do that? And the answer is you add the resistances, and I will prove that to you straight away. So if I have a current that flows into this resistor here, that same current has to flow out the other side and continue down through here, which is to say that if you have resistors that are in series, they will have the same current. The thing that's going to be different is that the potential difference across the resistors will be different. So if we call this one delta V1 and we call this one delta V2, what we know is that the sum, delta V, should be equal to delta V1 plus delta V2. And that's just how potential difference works. We can then use Ohm's law to rewrite delta V for this circuit right here to be I times the equivalent resistance. Delta V1 we can write as I times R1, and delta V2 we can write as I times R2. Hopefully you haven't forgotten that delta V is equal to I times R. That's what we're using right here. We can cancel out all of our R's, or our I's, sorry, to get finally that the equivalent resistance is simply found by taking the sum of the individual resistances. Quite easy to do. No matter how many we have, we just add them up when they're in series. That gives us the equivalent resistance. Anyone have any questions? It's pretty easy. Not too new because we just did the same thing with capacitors in parallel. You added them up, right? So the next thing to do is to look at parallel combinations. When you have parallel combinations, you're going to have something that looks maybe something like this. You'll have one resistor here, another resistor stacked on top of it, and then both of them connected up to an EMF source. In this one, what we know is the potential difference across all of them will be the same. So if we call this one R1 and we call this one R2, the thing that's going to be different is going to be the currents. So what we're going to say here is that suppose I call the current that flows in here to be I1, and then I call the current that splits off here to be I1, and the one that goes through this segment right here, I'm going to call I2. All right, and I'm just going to indicate the other places where these currents are. So this outer current is still going to be I. The current I1 flows all the way up through here, and I2 only flows across the center. What happens is that if you have a node like this, the current always has to split. Just like if there was water flowing in a river here, it would split into two different streams. And depending on what the size of those streams are, the water may be faster to the middle and slower to the top or something like this, right? But like I said, we know that the voltages of these things have to be the same. The other thing we know is that whatever current flows in here also has to flow back out here, or else you have a buildup of charge, and that wouldn't make any sense. So it must be the case that whatever current flows in has to be equal to the current that flows out. And what we can then do is to, again, use this equation right here and say that if we were to break this thing down into a circuit that only had one resistor connected up to that same battery, and the current flowing through that equivalent resistor we called I, this is Req, then, and this is still delta V, then what we can write individually for each one of these, I here we would write delta V divided by Req. For I1 we would write delta V divided by R1, and since they all have the same voltage, also for I2 we're going to write delta V divided by R2. And that allows us to say that if we cancel out all the delta V's, that our equivalent resistance is found by taking 1 over R1 plus 1 over R2. Boy, those look like K's, don't they? R1 plus 1 over R2 plus dot 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 to the negative 1. And that'll allow us to do resistors in parallel and resistors in series. And we'll do an example here. Any questions? Yeah, it's reversed from capacitors, because for capacitors, this would be parallel and this would be series. So it's exactly the opposite. If we had actually defined capacitance to be the inverse of what we defined it to be, then they would have been exactly the same, if that makes any sense. But we didn't. Okay, so equivalent resistance. So here we have a little network. It's super simple, but what we want to do is we want to basically take this one and we want to break it down into a circuit that has an equivalent resistance. And it says, find the equivalent resistance of the network and the current in each resistor. Let's do it. So we can break this one down because the 3 and the 6 appear to be parallel, right? Parallel, right? So we can go... This will still be 4, but this one is going to be a third plus a sixth, which I think is going to give us 2 over 6. 3 over 6. Yeah, this is going to give us 2. So this will be 2 ohms. It's still connected up to a EMF source. This is a ideal EMF source, by the way, because it has an internal resistance of 0. So here's our EMF of 18 volts. And then these two are in series, so we can break those down very simply as a 6 ohm resistor. Okay. And now we also want to find, this is going to be the equivalent resistance of the system. We also now want to find the current flowing in every one of these. So here, I'm going to say the current's flowing like this, and that the current here should be equal to E divided by R, because E is basically the same thing as delta V, and so we can use the equation delta V equal to I times R. And it's the same, by the way, because, again, R is equal to 0. Okay, so if E is I over R, then it's going to be, sorry, if I is E over R, then it's going to be 18 over 6, which is 3 amps in this case, right? As we move back to this position right here, I would argue that the current has to be the same flowing through this branch here, 3 amps. And that's because, well, they're in series. And one of the first things I said is that if you have series, you have to have the same current. Again, the idea would be that if the current flowing into this resistor was different than the current flowing out of this resistor, then you'd have a buildup of charge somewhere in here, and that wouldn't make any sense. So we can also then use this equation now and do I times R to find delta V here. So delta V for this resistor here should be equal to 3 times 4, or 12 volts. Delta V for this resistor should be equal to 3 times 2, or 6 volts. All I'm doing is just using that equation over and over again, just like we did with the capacitors. As we go back to this position here, delta V for both of these is going to be 6 volts. So our goal is to find the current through every resistor. Then in order to find the current through this resistor, we have to take I equal to delta V over R, right? So 6 divided by 3 ohms will give us the current, which is going to be 2 amps through this one. And then if we take the voltage of 6 volts and we divide by 6, that means the current flowing through here is going to be equal to 1 amp. And 1 plus 2 is equal to 3, which is good. And that's all there is to it, just like we did with the capacitors. I probably went through it a little faster, but it's because I expect by now you will already kind of understand what the process is. The only difference is, instead of with capacitors, we had delta V was equal to Q over C, right? So now delta V is equal to IR. It's just the same concept. It's just, different voltage. And pretty soon we'll put resistors and capacitors in a circuit together to see what they do. And that's when things start to get quite a bit more interesting. Can you say it or write it again? In series, same current. Yeah. Yep. It's right here. Series, same current. Okay, so let's get into the... I think what we're about to do is probably going to be the most helpful for you for not only your homework, but also for the lab that we just did. So that's going to be talking about Kirchoffs rules. So let's do that. Maybe someone here knows how to pronounce this better than I have. I've heard it pronounced Kirchoff. I've heard it pronounced Kirchoff. I've heard it pronounced Kirchoff. All kinds of different ways. No, Tian, that's not quite correct. Sorry. Yes, actually, possibly. Tian, possibly, yes. That might be right. However, I want you to... yeah, actually, that would work. It would work. It would work. But what I'm about to teach you will make it so that you don't have to... You'll be more confident in how to answer that question, if that makes any sense. Okay, so even though we just learned about how to combine resistors together, I'm just going to tell you right now that while you will need to do this from time to time, the majority of the homework that you're going to see, you're going to be using what we're talking about now, Kirchoffs rules. They are equivalent to each other, just so you know. Okay, so Kirchoffs rules work like this. There are two of them. One is called the junction rule. The junction rule says this: if I have a junction in a circuit, such as something maybe like this, and I tell you that the current flowing in this section is called I1, and I tell you the current flowing in this section is called I2, and the current flowing in this section I tell you is called I3, then at this point right here, which is a junction or a node, we know that the sum of all of these currents has to add to 0, and we're going to use the convention that inward flowing current, okay, is equal to positive current, and outward flowing current is going to be negative flowing current. The junction rule says that if I sum every single current, I'm going to get 0. The only way you can add things up together and get 0 is if some of them are positive and some of them are negative. So in this particular case here, that would work out to be I1 minus I2 minus I3 is equal to 0, okay? And again, the convention is that current that comes in is positive and current that goes out is negative, okay? So this one's negative, and this one's positive. It's pretty simple. Pretty simple idea. Anyone have any questions? That's the first Kirchoff rule. There's only one more. Only one more. It's called the loop rule, or the Kirchoff voltage rule. In or out of the junction, yeah. If it flows in, it's positive. If it flows out, it's negative. Actually, you can make in negative and out positive if you want to. You just have to be consistent. As long as you're consistent, it won't matter. Okay, the loop rule says that the sum of voltage drops around a loop has to be equal to 0. If we sum up all the voltage drops around a closed loop, they should be equal to 0. Now, this is much more easily shown by looking at a picture. So here we have a pretty simple network where I have two batteries with their internal resistances that are called R1 and R2. And the important thing to notice here is that this circuit cannot be reduced by using simple series or parallel combinations of resistors, as they say here at the top. That's when we have to use Kirchoffs rules. Can you see that? That even though this resistor is in parallel with this resistor, it's kind of not because of the fact that there's a battery there. That throws things off. Like, this resistor is in series with the battery, whereas this resistor is kind of like somewhat parallel to it, but not quite because there's another resistor here. So when you have a situation when you can't reduce it, you have to use the loop rule. How does the loop rule work? Well, there's 3 loops that are drawn in here. One of them is this loop here that's called loop 2. One of them is this loop here that's called loop 3. And then another one is this loop on the outside that's called loop 1. This is, in fact, the total maximum number of loops that you can actually draw in this circuit. Now, how do you actually use the loop rule? To use the loop rule, we have to have conventions. And these are the conventions right here. Okay? So I'm going to show you how this would be written down for the circuit that's written here, and then we're going to do an example. Ooh, this is kind of tough for this circuit, actually. There's already so much stuff drawn on there. So how about I draw my own circuit? It seems like a good thing to do. Suppose I have a circuit where I have a battery right here that has an EMF that I'm going to call E1. I have another battery right here that has, this is going to be positive, this is going to be negative. This has an EMF that I'm going to call E2. We're going to connect these up to each other, but we're also going to draw some resistors in here. On this part, we're going to throw a resistor I'm just going to call R1. I'm going to put another resistor right here that I'm going to call R2. And then I'm going to drop another resistor out here with no battery that we're going to call R3. Okay. And I'm going to show you how we do a loop rule. Okay. Now, in order to do this, I'm going to have to define currents flowing through my system. Okay. Now, I don't know what direction they're going to go. I know this is the positive side of my battery and this is the negative side. So maybe I just say, just because I feel like it, that I call the current flowing through here to be I1 and I say it points this way. And then say just because I feel like it, I make the current flowing through here, I call it I2 because I can call it whatever I want. And I can also make the direction whatever I want. So I'm going to make the direction here go this way. And then finally I have a current that's going to be flowing through this external resistor here, and let's say that I call it I3 and I draw that it goes this way. Okay. I don't know what the size of these batteries are because they're just symbols, right? This could be 10 volts and this could be 20 volts. I don't really know what they are. We're just going through this as a symbolic way to understand how this works. Okay. Now let's do a loop. Okay. The way that we write down a loop rule is that we start from some position. Like let's say that we start at this position right here. Okay. And then we are going to go around in a loop through my circuit like this until I get back to that same position. So we're going to start here and we're going to go around in a loop like this, and it has to be a closed loop. It has to be a closed loop. So that's my loop. And what the loop rule says is that if I sum up voltage drops around this, that it should be equal to 0. So how do we actually go about doing this? Use these. Let's look at what they say. They say that if I'm traveling in this direction and I have in my circuit an EMF source, and I go from the negative side of the EMF to the positive side of the EMF, I have gone uphill. Would you all agree with that? You've gone from a low energy point to a high energy point. Would you all agree? That if you're going from this position to this position here, in that direction, that you're going from the low energy or like the 0 volt side of the battery up to the high voltage side of the battery, right? As a result, you get a positive E out of this, okay? So this is going to contribute. I don't know if you can see it very well. In fact, maybe I make it just a little bit bigger. And then get rid of all this junk that I wrote on here. You're going to get plus E when you do that, okay? Plus E. Now, if you're traveling in the opposite direction, that is to say that if you start from this point and you go over to here in this direction, you're going from the plus side of the battery to the negative side of the battery, and you get minus E. See, this is where this is the answer up here. So the first one you get positive E, and for this one you get minus E when you go from plus to minus. Because you're going downhill, so the change in voltage is negative, right? You've gone to a lower energy state. You've gone from like 10 to 0. So just to remind you, if this was 10 volts and this was 0 volts, what would delta V be? Delta V would be 0 minus 10, which would be negative E in this case, or negative 10 volts. You understand? Do you all understand what we're doing here? Does it make sense? It's okay if it doesn't, because we're going to keep going. Next thing we would do is, what happens if I have a resistor? Resistors have voltage drops too. Now this matters what the direction of the current is relative to the direction of travel. If I travel against the current, it's like swimming upstream. If you travel against the current, you're swimming upstream. So notice the travel direction is going to be the loop. The direction of the current flows to the left. That's another thing. So we're going this way, but the current is flowing opposite to us. Then what you get here is positive IR because you're going upstream. It'd be like if you swim upstream, the stream can carry you back down again, right? Like you swim against the current. then the current will carry you back down. So it's like going to a higher energy state. So when the direction of travel is opposite the direction of the current, you get plus IR. And when the direction of travel is the same as the direction of the current, you're going downhill or downstream, and you're going to get a negative IR. Okay, did everyone follow along? If you go from minus to plus, you get plus E. If you go from plus to minus, you get negative E. If you go against the current, you get positive IR. If you go with the current, you get negative IR. That's it. Those are all the rules. That's all you need to know to solve these problems. So they're not going to make much sense until we use them, right? So let's use them. I'm going to call this loop 1 right here, okay? And I'm going to write down an equation for my loop 1 right over here to the right. I'm saying that I'm going to start at this location here, and I'm going to go from the negative side of the battery to the positive side of the battery. What do I write down? If the battery has an EMF of E1, do I write plus or minus E1? Which one do I write down? I'm going in this direction, so I'm traveling in that direction, right? Plus, right? Plus E1. Okay, so let's get rid of that negative. Next, I go across the battery, I go across this resistor, and I notice that I've defined the current flowing in the circuit to be I1, and I go across R1. So which one does that correspond to? Am I going opposite the direction of the current, or am I going the same direction as the current? Current goes this way, loop goes the same way, we're going the same direction. What do we write down? Someone else answer? Do I write down plus or minus I1 R1? Yep, so we're going to write minus, keep using yellow, minus I1 times R1. All right, are you all still on board here? Okay. Now we get to the next, basically the next thing we encounter as I'm going around this loop is this resistor here, R2. I notice the current is flowing in the same direction as R2. Do I write plus or minus I2 times R2? Same direction, so the loop is up, the current is up. So now we do negative again, right? In travel in this current direction, you get negative IR. All right, one last thing here. I have the battery, E2. We're going from negative side to the positive side. So again, we're going to get plus E2. All of this equal to 0. There you go. All right, let's do another loop. Let's use blue. Let's do this loop. Let's do it just a little bit differently. Let's start here, and let's go in the loop around this direction. Okay, so my loop is going to go like this. It does not matter how you do this, because it'll all work out regardless of how you do it. If I start here, and I'm going against the current, I'm going to have an I3, R3. This is loop number 2. Is it going to be positive, or is it going to be negative? I3, R3. Am I going to write positive or negative for this one? Positive, because we're going opposite the direction of the current, right? Upstream. Come around here, I have an E2. Am I going to write positive or negative E2? I'm going from the positive side to the negative side now. I'm going from here down this way. So I'm going to get negative E2. Negative E when you go from plus to minus, right? And then finally, I have I2, R2 here. Is it going to be plus or minus? It's going to be plus because we're going opposite the direction of the current. See, loop is down, but the current is up. And that's all equal to 0. What about the junction rule? Could I have written a junction rule for this circuit? Of course I can. I can look either at this junction right here. Let's look at this one. This one has current I1 flowing in, I2 flowing out, and if you follow I3, it's also flowing in. Now, you'll notice that if I told you the values of the batteries, E1 and E2, and I told you the size of the resistances, we've now constructed a series of 3 equations that have 3 unknowns, which are I1, I2, and I3, that we can now solve for. And that's what we use these equations to do, is we use it to solve for unknown currents, unknown voltages, whatever it is that you happen to want to do. So we're going to do some problems, but I just want to stop for a second and see if everyone's on board with what we're doing here. It'll make a lot more sense with numbers. This is just the theory. Any questions before we go on? Oh, this would have been plus I3, actually. Plus I3. It's because in this one right here, it's negative because the loop was down and we were going from the positive to the negative side. So it's this reason right here. Hopefully that makes sense. Okay, let's look at a problem. Here's a problem. So our goal here is to find the current flowing through each resistor. All right. Now, I'm going to put the rules right here. Okay. And what I want you to try to do in this picture, what we're gonna do is, first thing that we're gonna do is we're gonna label currents so everyone's on the same page. But I want to emphasize that what I'm about to do is arbitrary. So, in order to solve for the current through each resistor, we need to, on our picture, label each current that we want to use. So what I'm going to do is just from top to bottom, I'm going to label the currents I1 in this branch. Realize that this I1 actually flows from C to F to E to B. I'm going to make the current in the middle branch to be I2. And I'm going to make the current in the bottom branch to be I3. Okay? I chose all of them pointing to the left. I did not have to do that. Okay? I did not have to do that, but I did. And I just want to emphasize that if, for whatever reason, you think that you have to think about the direction of the current before you write it down, you're wrong. You can just pick a direction. And if at the end you picked the wrong direction, your answer will come out as negative, so it doesn't really matter. So here's what I want you all to do. We're going to do 2 loop rules. Okay, so we're going to draw a loop, and I'm going to tell you what the direction of the loop is going to be. We're going to do counterclockwise for both of them. This is going to be loop number 1, and we'll do a loop down here that we're going to call loop number 2. I guess what I would like for you to do is for loop number 1, start at point C, and for loop number 2, start at point D, and then do your loops like that. And what I want you to do is I want you to try to write down the loop rule for each of these, okay? And let's start off by, let's write down the junction rule together. So the junction rule in this case, I1, I2, and I3 are all going into the node. So the first equation we're going to get from the junction rule is going to be I1 plus I2 plus I3 is equal to 0, okay? Because they're all flowing into the node. So we get that equation. What I want you to do is to write down the 2 loop rules. I'll give you a few minutes to do it because it takes some time. Does that make sense to everyone? You think you can do it? Do you want the other one as an example? I don't know if that's going to help. Might confuse you more. I don't know. Maybe we just. What do you think? Should I leave this example here so you can compare, or will it just confuse you? I think I want you to just look at the picture here and just focus on this. So we're not actually going to do this part. All I want you to do is to write down the loop rule for loop 1 and loop 2. Do you all feel like you can do that? Do you feel like you can do it after this this very brief description? Give it a shot. Give it a shot. I will give you... Let's see what happens after 3 minutes. Let's see how everyone's doing. Yeah, it doesn't matter, Tom. I picked directions. It doesn't matter. You just pick a direction, write it down, and then go from there. The directions I chose, I could have flipped it. It didn't matter. Is that clear? It's just random. I just randomly picked them. I picked them all go left. You can pick them all go right. You'll get the same answer as I will. Except yours will be negative, mine will be positive or something like that. Makes no difference. Same, yeah, the loop, you just pick a direction and go with it. Doesn't matter. Does not matter. Yep, no problem. Alright, was that enough time? Did anyone get an answer for like at least one of the loops? Or do you need a little more time? I'll give you a couple more minutes. All right, let's see how y'all did. So we'll go through these. Well, there's some. You got to get the. You have to include the numbers on these ones. Okay, so let's go through our loop rules here. So let's start with loop 1. Here, let's write it like this. Let's put this up here. Go down here. Okay, so for loop 1, I said to start at point C. So what you should have gotten is, as we move to the left right here, there's a 6 ohms times I2. And we're going in the same direction. So you should have a negative sign here because I2 and the loop direction are the same. So that corresponds to this one here where you get negative IR. Then we come to this, you have a positive here and a negative here. So that means we're going from plus to minus. So we're going to get a negative 10 volts. Again, when you go from plus to minus, you get negative 10, negative E in this case, which is 10. When we get to this point right here, we see that the current I1 is flowing down, but the path that we're traveling along is going in this direction. So that means that we write down plus 4 ohms multiplied by I1. And then we get to here, we have a 14 volt battery, and we're going from the positive side of the battery to the negative side of the battery. So we're going to write negative 14 volts. And that's equal to 0. That's the first loop. I'm going to write this in a little simpler way. I'm going to drop all the ohms off of everything. So it's just going to be 6I2. And let's combine together the 10 and the 24. So we'll get minus 24 volts. And then we have 4I1, which is positive. So we'll do plus 4I1. Just because if we include all these units on here, it can get kind of confusing. All right, so that's our equation 1 right there. I'm just going to box it because we're going to use it in a bit. That's our first loop. We also got this equation from our junction rule. All right. Okay, let's do another loop. We'll do it in green. So loop 2. Any questions about loop 1? And do you all agree? Why 4I1? There's a 4 ohm resistor right here. There's a current I1 flowing through it. So you have to write 4 times I1. Does that make sense? Remember, what we're doing here is we're writing potential differences, and one of the ways to write potential difference is current times resistance. So here we have current times resistance. You know, if I want to be really accurate here, as I move from this line to this line, I guess technically what I did was I divide through by ohms. So this should technically be like amps now. I'm going to leave it as volts, but it's almost like I have to divide by ohms right here. That'll matter when we do the... let's just do that. We'll just divide through everything by 1 ohm, and I can get the volts over ohms here, which means this is going to basically be negative 6I2 plus 4I1 minus 24 amps, if we're going to do it this way at least. Could I start at a different point and get the same result? Definitely. It does not matter where you start. You can try it. Try it yourself. You'll still get the same answer. All right. For loop 2, what we have is we start at point D. We have I3 times 2. That's going to be negative 2I3. Okay, I guess I'll leave the ohms in for one line. So 2 ohms times I3. Negative because we're going with the current. And then we keep going this way. We get to point B. We get to here. We're going from the negative side to the positive side of the battery. So we're going to get plus 10 volts. And then we're going against the current. So we're going to get plus 6 ohms times I2. That's going to be equal to 0. Let's divide through by ohms again. So we're going to get negative 2I3 plus 10 volts divided by ohms plus 6I2, which can then be written as negative 2I3 plus 10 amps plus 6I2 is equal to 0. So really we've got that equation, and we've got that equation, and we've got the other equation that's circled up here as well. Does anyone have any other questions before we try to solve this? No one? Okay, so we want to solve these 3 equations. And because this is just a pure math problem at this point, what I'm going to do is we're going to copy paste each of these equations down here. So we've got that one. We've got that one. And we got this one. They form a system of 3 equations with 3 unknowns. We're not going to get to this today, I don't think. And we basically just need to solve those 3 right there. And we can do that any way that we want to. What I notice here is that when I look at the second equation, it has I1 and I2. And this equation also has I2. So I2 is the one thing that is the same. Or sorry, I2 is the one variable that shows up in every single equation. So I think what I want to do is I want to eliminate all the other variables. So what I'll do is I'll solve this one for I1. So we're going to get something like, let's see, we'll have 4I1 will be equal to 24 minus 6, or sorry, 24 plus 6. So 24 amps plus 6I2. And then we can divide through by 4 to get that I1 is equal to 6 amps plus just I2 with no coefficient. Is it that simple? No, it's not even correct at all. Sorry about that. 6 divided by 4 is like 3 divided by 2, which is like 1.5. That looks better. Does that look okay, everybody? Same thing over here. So we'll subtract the 10 amps and the 6I2. And then we'll divide through everything by -2. So we'll get I3 is equal to -10 over -2 is going to be 5 amps. And then 6 over 2 is going to be 3. Or -6 over -2 is +3. I2. Like that. And now we should be able to plug both of those. The I1 can go into there for I1, and the I3 can go into there for I3. So what we're going to get if we combine them all together using I1 plus I2 plus I3 equal to 0. I1 is 6 amps plus 1.5 I2 plus I2 plus I3 is 5 amps plus 3 I2 equals 0. So now we only have one unknown, which is I2. And if we add together all of our coefficients, we're going to get I2 multiplied by 1.5 plus 1 plus 3. And all of this should be equal to, looks like -11 amps. 6 plus 5. So we add these together, we have 3 plus 1 is 4. 4 plus 1.5 is 5.5. So we'll see that I2 is equal to -11 over 5.5 amps, which would be equal to, if I multiply by 2 over 2, this becomes 22 over 11. So is that 2? Yeah, it's 2, right? So I2 is -2 amps. Let's solve for the other 3. According to this equation right here, I3 is then going to be equal to 5 amps plus 3 times -2 amps, because that's what I2 is equal to. So 5 minus 6, I3 is equal to +1. No, -1. Getting these nice round numbers is probably not by chance. And finally, our equation for I1, which you can see right here, is that I1 should be equal to 6 amps plus 1.5 times I2, which is -2 amps now. And we end up getting that I1 is equal to 3 amps. So there we go. There we go. So we end up getting I1 is 3, I2 is -2, I3 is -1. Let's write our answers up here. So I1 was 3. I2 was -2. And I3 was equal to -1 amp. So those are our answers. Let's look at our picture again. What does this mean? So I drew the direction of I2 to point to the left. My answer says that it's -2 amps, which means that if I were to plug an ammeter in there, that's what it would read. So the current's actually flowing this way. Wait a minute. Does that work? I think my thing's backwards, right? If I point... Yeah. Okay, it looks right to me. The question is, does it look right to you? I don't know. I can draw it on the picture. The current's actually going that way is what I'm trying to say. Same thing for I3. I said the current was flowing to the left. It's actually flowing to the right. So, anyway, that is an example of a Kirchoff's law problem. I think we're kind of out of time, aren't we? Yeah, we're pretty much out of time. One thing I'll say is there's another method that you can use to do this. So if we take our 3 equations here, no, I definitely said that. That's correct, Evan. It does not matter how you write the currents, whether you believe it or not. You'll always get the same answer. Just works out. So what I can do with these is I can basically turn them into a matrix, okay? And the way that I'm going to write my matrix is like this. I'm going to put all the constants on the right-hand side, and I'm going to rearrange them in a certain way. So I'm going to rewrite this equation as 4I1 minus 6I2, and then I'm going to add a dummy term here, 0I3 is equal to 24. I'm going to rewrite this one in the same way. This doesn't have an I1 term, so I'm going to write 0I1 plus 6I2 minus 2I3 is equal to negative 10 amps. And then this one I don't have to change, okay? So this has 1, 1, 1, basically, right? And now I'm going to write a matrix that's going to be a 3x4 matrix, and I'm just going to put my coefficients in here. So this one's going to go in the first line. The coefficients are going to be 1, 1, 1, 0. This one's going to go into the second line. The coefficients are going to be 4, negative 6, 0, and 24. And in the third and final line down here, I'll put these coefficients, which are 0, 6, negative 2, and negative 10. And then what we're going to do is we're going to take this matrix and we're going to do something that's called reduced row echelon form. Have you all heard of that before? Probably. This is something that you can do on your calculator. Yes, that's exactly right. It's on 100%. Travel direction is the direction of the loop, and the current direction is the direction of I, and it's random. Yes. That direction of I is up to you. You just pick direction and go with it. You just got to be consistent and stick with it. Okay, so for the next part, I'm going to show you how to do this. You're going to need to use your own calculator to do this. I don't have a TI that I can show you to do this with. And I'm just going to use an online calculator to do it. So you're welcome to find one of these on the internet if you want to. There's a lot of different ones that you can find. I don't know what just happened to my notebook. It just started a random new page. Okay, so we're still here. Okay. All right. To do this on your calculator, what you have to do is you have to make a matrix, put this into the matrix. Okay. You go to the matrix editor mode and you type this matrix in basically. And then you go back out, and if you go into your matrix math settings, if you poke around, you'll find a function that's called RREF. And all you need to do is you just need to put the matrix inside of this. So basically you just take this and you put it into a matrix in the editor, and then you run this function, and it's going to output something that I'm going to show you right here. If you need help figuring out how to do this, there's all kinds of information on the internet about how to do it, but I can also show you when we're in person. It's hard to show you when we're on the internet, but so what I'm going to do is, I'm also not going to show you the calculator I'm using, because last time that I did that, I got one of my videos taken down, and I got a strike, I guess, which means that they can turn my channel off. I don't want that to happen, so I'm just going to do this off screen, and I apologize that I can't show you what I'm doing, but like I said, I can show you after class, I guess, just as long as I don't record it. And I'm going to click calculate, and what it's going to spit out is, oh wow, this shows all the steps, which is pretty amazing. What it's going to happen is that the output is going to look something like this. Your calculator will work the same way, so you're going to end up with a matrix that's going to look like this. It's going to be 1, 1, 1, 0, 0, 0, 0, 0, 0, and over here on the left you're going to have the answers, which in this case are 3, negative 2, and negative 1, which is the same answers that we got. What this says is that I1 equals 3, I2 equals negative 2, and I3 equals negative 1 amps, amps, amps. And that's where we're going to stop for today. Next time we'll continue with Kirchoff's laws and possibly get into talking about magnetism? Is that the next chapter? It is. Wow. Good. Okay, so I hope you all have a good week. If you haven't done lab E-3, you're going to be doing the lab next time. Okay. Wait, what are you booing about, Giselle? I'm sure it's not that important.
She was saying boo to you getting a strike on YouTube. Yeah.
Okay, so that's I'm going to stop recording.